Hello everyone. In this AV we are going to talk about chapter 16, that is fluid pressure. To start off with the chapter, first let us understand the term fluid. So please remember that fluid is anything which or that can flow. When we say that anything that can flow is a fluid, what we mean by it is, firstly, it will have no definite shape. If it has got no definite shape, then what it will do is it takes the shape of a container. Now, so with this definition, what we come to know is both liquid as well as gases, they will be under the section fluid, or they can be termed as fluid because they fulfill these criteria. Now we will try to understand what is fluid thrust and fluid pressure. So for that, please look at this figure. Here we see that a material or a box or a body is being immersed in a fluid. So here we see that the force which is being applied by the fluid on this box is normal to the surface of the box. Here this force which is being applied is normal to the this face. Similarly, all the forces that we are seeing here, they are always applied normal to the surface. So when the fluid is at rest and the force applied or the force exerted by the fluid is normal to the surface, that is known as thrust. Thrust is nothing but normal force, or the force applied normal to the surface. Fluid pressure is nothing but thrust applied per unit area. So thrust is nothing but the force. So we have the formula for pressure of the fluid, that is pressure is equal to force per unit area. So SI unit, to find the SI unit of force is nothing but Newton and area is meter square. So SI unit for pressure is Newton per meter square, and the dimensional formula would be ml minus 1 T minus 2. This is the dimensional formula for pressure. Now, based on this formula, we know that pressure is equal to force upon area. So if we want to reduce the pressure, then we have to increase the area, and when we want to increase the pressure, we have to reduce the area. This application, or this practical application, you can find when you look at nails or pins. You will find that they have very small area by having pointed or sharp tip. That's how even if we apply small force, then because of less area, the pressure increases. Same is the case with railway tracks. Railway tracks are laid on very large sized wooden slippers so that the pressure decreases. Why? Because the area is much larger. Now, when we talk about the pressure due to a liquid column, please check this figure. Here we have a body which is dipped in the fluid or liquid. So here we find that there are three forces which are acting on this particular body which is immersed in the fluid. What are they? This is the first force which is acting on the body, that is pressure 1 multiplied by the area for this. Then we have pressure 2 multiplied by the area, and then we have the weight of the body which is also acting downwards. So what we see is these two forces are acting downwards, and this particular force, that is P2A, is acting upwards. So to find out the total force, what we do is we will add these two up because they are acting in the same direction, and then we will subtract this. So that we find that P1A plus the weight of the body, that is mg, they are acting in the same direction, so we add them up, minus P2A. And since the net force on it must be 0 because the liquid is in equilibrium, so we equate it to 0. Now we find P1A remains as it is. Mass is nothing but area multiplied by the height of the column, you can check this, and multiplied by the density of the liquid, and then this G minus P2A. So here, if we take A common and simplify this equation, what we find is P2 minus P1 will give us nothing but rho hg, that is the height of the column multiplied by the density multiplied by the acceleration due to gravity. So this is nothing but the actual pressure that the fluid will exert on a liquid. Now, after deriving the equation for the pressure which is being exerted by the liquid column, we come to something called Pascal's law, and this law is very important when we talk about fluid pressure. So if we see this figure, what Pascal's law tells us is the pressure which is applied on a small part of the body in a liquid will be equally transmitted all over. Okay, the exact statement will come to it. Before that, let's understand the mathematical part. Looking at the figure, we know that F1 is equal to F2. Here, force exerted on face C is equal and opposite. These two forces are equal and opposite. So F1 is equal to F2. Now we assume that pressure 1, that is P1, is being applied here and P2 is being applied on surface D. So force 1 is P1A and force 2 is P2A. Since F1 is equal to F2, so automatically pressure 1 is equal to pressure 2. This is what Pascal's law tells us, that pressure in a fluid or a liquid in equilibrium is the same everywhere, or it will be transmitted everywhere with the same force without any loss. Now, what are the applications of these laws? These laws are applied for hydraulic brakes. That hydraulic brakes, we are no longer using it. And then we have hydraulic lift. So what we see in hydraulic lift is, for a smaller area, if we apply a small amount of force, then it is equally transmitted throughout the fluid, and through a pipe it is connected to a bigger area. So automatically this upward force is going to be very high, and that can be used to lift the loads. As this is not in the syllabus, we are not going into the details. Now the mathematical part is, the pressure is equal to F1A1. We are talking about the pressure for this column where we need to apply smaller force. So that will be equally transmitted to the larger area, that is A2. and this fluid will exert an upward force, so that F2 will be P into A2, that is pressure into A2. So from the first equation we know that pressure is nothing but F1 upon A1. So we find that F2 is equal to F1 upon A1 multiplied by A2. So here, as we know that A2 is greater than A1, so automatically F2 becomes greater than F1. So these are the applications of Pascal's law, that is hydraulic lift and hydraulic brakes. Now here, if you look at this figure, what does Pascal's law tell us is, in an enclosed liquid, that is the liquid is at rest, then or in equilibrium, then if the pressure is increased in any part of the liquid, then it will be transmitted equally in all directions or to all parts of the liquid. But if we look at the actual term or actual expression for pressure, then we find that Pascal's law does not take into account the gravity part of the fluid. It does not talk about the gravitational part or the gravity of the fluid. So the actual formula for pressure is given as P2 equal to P1 plus rho hg. We have done it before in the starting of the video. Here pressure is equal to P2 minus P1 rho hg or h rho g. So from here, this minus P1 we are taking to the other side, so we can write the pressure or P2 is equal to P1 plus h rho g. So we have to keep in mind that the liquid pressure will be the same at all points at the same depth, but below the liquid surface, as we go deeper, then there will be something called atmospheric pressure that we have not talked about. So because of that atmospheric pressure, the overall pressure will be given as P equal to P naught plus rho hg or rho gh. This term P naught represents atmospheric pressure, which will increase as we go deeper into the liquid. So because we will have to take into account the atmospheric pressure, that is why once the diver goes very deep into the sea, then he or she needs to take care of the pressure also. But we also have to keep in mind that the pressure will not depend upon the shape or size of the container. It will only depend upon the density of the liquid and the density of the liquid and the h, that is nothing but the depth to which we are diving in. So whenever a body is being immersed in a fluid, or a diver or a swimmer is getting inside the pool or water or pond, anything, then the liquid will exert a pressure or a force in the opposite direction. The simplest way of experiencing it is, take a mug or a jug, turn it upside down and try to immerse it in a bucket full of water. You will experience some upward force. Now that upward force is nothing but, it is known as buoyant force. That buoyant force will depend upon how much volume you have immersed in the liquid. How much volume of that mug or jug that you are holding, how much of it you have immersed in the liquid. The more volume you immerse, more will be the upward or the buoyant force that we are going to experience. So here we come to an important law which was given by Archimedes, which is known as Archimedes principle. Sorry. This law says that whenever we immerse a body or an object in a fluid, then we are going to experience an upward force. And that force that we are going to experience will depend upon the volume of the body that is being submerged. It will depend on the volume of the body immersed in the fluid. Next, it will also depend upon the density of the fluid or liquid. So this we will denote it as sigma. And finally, it will also depend on acceleration due to gravity. So there will be a weight loss, or we can also say that Archimedes principles another statement is, when a solid body or when an object is partially or fully immersed in a fluid, then it is going to experience a loss in its weight. It's going to weigh a little lighter than its actual weight. So that is because of the upward force. So let's calculate the upward force so that we know how much weight it's going to lose. So that force is nothing but equal to the weight of the liquid that we are going to displace. So that is equal to the volume multiplied by density of the liquid, that is sigma, multiplied by the acceleration due to gravity. So volume is nothing but mass upon the density of the object or the density of the substance multiplied by the density of the liquid multiplied by the acceleration due to gravity. So this is the upward or buoyant force. So the actual weight that we are going to feel if the body is immersed in a fluid, or we call it apparent weight or effective weight. Effective weight. This is denoted as W prime. So that is going to be the actual weight minus the upward buoyant force. So that is nothing but mg is the actual weight minus this portion, that is mass of the object multiplied by the density of the liquid multiplied by the acceleration due to gravity and divided by the density. So if we have mg in both the terms. So if we take mg common, then we have 1 minus density of the liquid upon the density of the substance or the density of the object. So please note that this is the reason why some of the objects or the body can float on a particular liquid and some bodies they cannot flow. So this depends on this factor. If the density of the liquid is lesser than the density of the object or the body, then the body will sink. Body sinks. Similarly, if the density of the liquid is greater than the density of the object, then the object or the body will float. And finally, it might happen that they are equal to each other. In that case, body will float, but the entire body will be submerged in the fluid. It will float, but the body will not be, any part of the body will not come above the surface. Submerged. So these conclusions is being drawn from what we know, call it as Archimedes principle. That's all in this AV. Thank you so much.